Hello, it's Keith here, and this is lesson 53 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at the NeoGeo again today, and we're looking at Mintile, which is my multi-platform tilemap code. Now, we're going to be using the fix layer, which is really designed for sort of font and text graphics, simple on-screen displays for the NeoGeo, but I think this is a very easy way to get started with graphics and just programming in general on the NeoGeo. Now, the problem with the NeoGeo is that it doesn't have a tilemap in the sense that most systems have, and in fact the closest thing it does have to one is the fix layer, which is effectively a non-scrolling tilemap. Now, the way that the games on the NeoGeo get around this problem is they actually combine lots of hardware sprites together into huge grids, and multiple of these can make multiple layers. We're going to look at that in a later lesson, but this is the sort of simpler one, which is just using the fix layer to simulate our game tilemap. So we've got our character moving in 8x8 jumps here, because this character isn't done with hardware sprites, it's just done with the fix layer, and we can scroll the tilemap in 8 pixel blocks, because again that's all the fix layer can do. The fix layer can't just do smooth scrolling, and there's only a single layer and things. So as I say, it's not really designed for a in-game tilemap, but I think if you're just getting started, if you're just having a play with 68000 assembly, I think it's a good place to start because it's a lot simpler. Okay, well, let's go over to our code and let's take a look. Now, the first thing we need to discuss is how the actual graphics get to the system, and you'll notice that I'm getting a warning here saying, oh, the XML file has changed, because my scripts automatically update the XML file. Now, when we want to get graphics data to the hardware on the NeoGeo, not the NeoGeo CD, just the regular NeoGeo, we actually have to do this within the ROM cartridge, and I'm using MAME as my emulator, and this uses an XML file to define the component files and the memory addresses which they're loaded into. You see, on the NeoGeo, it actually has video ROM, not video RAM, for its pattern definitions. So there's no way we can define these in code. We can't load some bitmaps in and then stream them to the VRAM, because there is no VRAM. As I say, on the CD systems there is VRAM that works like most of the systems, but generally there isn't. And so what we have to do is we have to define the data area for the fix layer, and then we have to load in our various files here, and you can see here we've got the Mintile Chibico fixed layer data here, and the YQuest data, which I'm just using as some dummy background tiles as an example. And we're loading these into various memory addresses here. You can see we're loading them into 16000 and 17000 here. These are the offsets, and these are the destination memory addresses, and you need to make sure those memory addresses that you load your data into match the tile numbers that you're using to display, otherwise you simply won't see anything, which probably not going to be very good if that happened. So that's what we have to do. Now you can see here we're defining these the characters here: test Chibico reverse here, and test sprite here. Now the reversed version is the XFlip version. You see the fix layer can't actually XFlip, and so we're defining a second set of tiles that are XFlipped here. And then we're also defining our background sprites here as well with this test sprite here, which is the effectively actually the that's actually this YQuest data here. So that's the correct memory addresses for those two there. So that's how we're defining our data to use. Now, what we're not going to look at today is we're not going to look at all the code that's really been covered in the simple series before. We're not going to discuss the header. We're not going to discuss reading the joystick. We're not going to discuss moving, reading the joystick and moving the X and Y coordinates of something around the screen, because that's all been done before in the simple series, and I'm not going to cover it again here. What we're going to discuss is the graphical routines that are getting the job of getting the data to the fix layer done. Now, in my Mintile series, most of the code is multi-platform, so it's all shared on the 68000. It's one piece of common code, and I've got a set of tutorials on that, and there's a link on my website, and there's YouTube videos on that, so please see those if you want to see the general code. Now, the way the general code communicates with the platform specific code is it breaks the job up into individual strips. Now, whether we're drawing an entire tilemap or just a little sprite, it's all done in horizontal strips, and so we start from the top left corner of our object, be it the screen or a sprite, and we draw from left to right, move down a line, draw left to right, move down a line, and we repeat until our object has been drawn. That's how we do things, and so that's what this code is going to do. Now, if we're drawing the entire screen, then basically we're going to start from the VRAM address of the fixed layer itself, which is 7000. Now, we're adding 4 plus 32 times 4, and that's to center the virtual tile map, if you will. The virtual screen is 256 by 192. That's a very common minimum resolution on a lot of systems, and so the systems that have actually a bigger screen like this one, we're actually centering that screen, and so I did calculations there to just center the screen. The fixed layer starts at VRAM address 7000, so that's what we've got there. Now, when we actually want to draw the sprite, though, we need to calculate the top left corner before we start drawing it, and that's what this code is going to do. So first, we're starting with that screen-based value there, which is, as I say, starting at 7000 in VRAM there. And then what we're going to do is we're going to add the X and Y position. Now, the X and Y position are in logical units, which is pairs of pixels. I use coordinates in pairs of pixels. It works very well on 8-bit systems with the 256 by 192 screen coordinates. So we're going to be working with that here. But of course, what we're going to need to do is we're going to need to convert that to a number of tiles. And so we're rounding to a number of tiles here by zeroing the bottom 2 bits here. And then what we're actually going to do next is we're going to basically calculate the VRAM destination. Now, rather unusually, most systems always go from left to right down the screen, but the fixed layer is actually rotated by 90 degrees, and so it actually goes, consecutive VRAM addresses go down the screen. And so to calculate the X position, we're actually going to take our X coordinate and multiply it by 32, because there's 32 vertical tiles in a line. And then for our Y coordinate, we're actually effectively going to just multiply it by 1. So that will calculate our VRAM destination. Now, when it comes to actually drawing our tile maps to the screen, we have different kinds of tile map. We have the background tile map, which looks something like this. This is the background data. Now, in here, you'll notice there's no zeros, but our sprite has a miniature tile map, and this one does have some zeros. Now, a 0 in the sprite means a transparent part of the character. You'll see around the feet there's no tiles being drawn, and that's what these zeros down here are. But the tile map here is actually a cache of changes, and once a tile's been drawn to the screen, a 0 is written back into the tile map, and so when we need to scroll, we need to refill that with new data, and we do that based on what old tiles actually need redrawing and which ones haven't changed. On the old 8-bit systems with the bitmap screens, that's very important because it saves a lot of time. So this is actually a cache, and a 0 in here would mean no change needs making. Okay, so what we're going to do here is basically we're going to now draw a strip to the screen, and we've got various registers defining the strip job. So what we're going to do first is we're going to select our VRAM destination. VRAM is in A6, and so we're moving that as a 16-bit value to this port here, and that selects the VRAM destination. What we're doing next is we're loading in the tile number from A2. If that's a 0, then this is an empty tile and we're going to skip it. So we will just jump down to here and we would move to the next tile. But what we're going to do if it's not 0 is we're next going to check tile clear. Now, if tile clear is 0, then we're going to do nothing. And that would be the case if it was the sprite we were drawing, because we don't want to change anything. But if we're doing that background tile cache, then we want to actually clear that when we draw it. So we would write a 0 bytes to the tile map there. Now, what we're going to do next is we're going to add A5. A5 is effectively the offset for this tile map. The sprites and the background have a different set of tiles, and so they have a different offset, and you saw them actually. These are the offsets that will end up being used up here, so that's the calculated offsets there. So that's what we will be using. And so basically once we've done that, we're then moving to the next tile in A2. That's our source tile map that we used up here. And we're then writing the 16-bit tile number to 3C002, and that is the companion port to this one here. This one selected the VRAM destination, and then we write a 16-bit value to this port, and that writes it to the address that we selected. Okay, so now all we need to do is we need to move to the next tile in VRAM. We do that by adding 32 to move 32 tiles across in VRAM, but remember we go down the screen, so this is effectively moving us across one horizontal tile by adding 32. As I say, it's backwards to what most systems do, but it's absolutely fine. And so that will move us across the screen by one tile, and we're then repeating until we've done the entire strip, and then once we've done the strip we return. The empty tile version just skips over the current tile and moves on, so it just doesn't do any actual data work. Now, do strip reverse is the version for the X-flipped character, because our character can turn around. This game engine was designed to do a simple Street Fighter parody, and so we needed to be able to X-flip our characters, but we didn't need to Y-flip them, which is why Mintile is limited in that way. I am working on a successor called Maxtile, which is far more advanced and will support X and Y-flip, and as a lot of other things as well. So you can see our characters can X-flip around. Now, the code that actually does this work is actually exactly the same, really. So what we've got here is our code to actually do the reverse version here, but you'll see we're actually loading the data in the exact same way. The only difference in this code is we're actually going from right to left in the source tilemap, because we draw from left to right on the screen, we work backwards through the tilemap. So instead of adding 1 to A2, we're subtracting 1 from A2 here as we work through the source data. The way that the actual graphics are being flipped is we have an alternate version of the tiles within our pattern data. So we've got a pointer here to the reversed versions, and the multi-platform code is actually selecting on the NeoGeo these reverse tile data as the X-flip source. That's the X-flip source, that's the regular source, and those are given values that represent the tile numbers and the respective offset for the regular Chibico at that address there, all of that lot, and then the reverse version adding 64 to skip the unflipped tiles there. So that's how we're doing X-flip on this system. As I say, the fixed layer isn't really very advanced. It was intentionally not very advanced because it's not really designed to do what I'm doing with it today, which is fine. As I say, I'm not really suggesting this as a solution for a, you know, if you were aiming to make a commercial game, you don't want to use the fixed layer for doing all your graphics, but you will probably want to use the fixed layer for something. And also, as I say, if you're just looking to get started, if you're just looking to make a Pong game, then the fixed layer is going to do just fine for you, and it avoids you having to worry about the complexities of the sprites. So I think easier to get started. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.